Thanks, Victor, for the nice introduction, for the invitation. It's been really nice talking to all of you, learning what kind of research goes on here at UMD. So indeed, I will be talking a bit about dualities in one-dimensional quantum lattice models. From the point of view of tensor networks. So my background, I'm a PhD student in the group of Frank Verstraeten. We do tensor networks. That's pretty much all we do. And we try to apply these to any and all problems we encounter. And my own research is more situated in the kind of the theory of tensor networks, studying how symmetries work in tensor networks, and now also how dualities work. So I hope I can convey some of that, some of the things we learned today. Right. So some outline. I'm first going to talk about symmetries, because it turns out that dualities are very much tied to the symmetries of a problem. Then I will explain what we mean with a duality, because there are some notions of duality floating around, just to establish what notion of duality that we are using. Then I'm going to talk about matrix product operators. This is going to be a bit more tensor network oriented, but no worries, I will explain what I mean by that. Matrix product operators both as symmetries, but also as dualities. It turns out that these give you a nice representation of both of these concepts. We're going to illustrate this with some examples and then have some conclusion. So this talk is based on a recent paper that we wrote together with Clément Delcan, Gerardo Ortiz, and Frank Verstraeten in December of last year. Using a lot of the mathematics that we developed in an earlier paper that we wrote with Jürgen Fuchs, Jutta Hagemann, Christoph Schweigert, and Frank Verstraeten. Here, Jürgen Fuchs and Christoph Schweigert, these are proper mathematicians, but they are used to talking to physicists. So we were able to collaborate on this project. It was a lot of fun, and everything I know about category theory I learned from them. Right. So what do I mean by symmetry? I suppose you all have some idea of what symmetry could be. I'm interested in global symmetries. These are symmetries that are, sorry, do I have to do something or? Okay. That's, I suppose, what you get if you advertise the talk on. So we are interested in global symmetries, which are represented by operators that commute with a Hamiltonian, and that in the most general case form a fusion ring. So these operators, we denote them as OA. They commute with the Hamiltonian, and the product of two such operators gives me a linear combination with integer coefficients, these n, a, b, c, these are integers, of MPOs that I already had. This includes groups symmetries, in which case this n, a, b, c for a given a and b, c would be unique, but it also includes more general symmetries. In the case that these are groups, these symmetries are unitary, but in the more general case, for example, Fibonacci, for those of you that are familiar with that, those symmetries are not invertible anymore. They don't have an inverse. Therefore, they are not unitary because they're not even invertible. In general, if you have some global symmetries, these global symmetries decompose the Hilbert space into irreducible representations of that symmetry. That's something that you're familiar with, for example, for SU2. If you have a Hamiltonian twin SU2 symmetry, then your Hilbert space decomposes into different charge sectors under this SU2 symmetry, which are the different EFs. Slightly more generally, you can include twisted boundary conditions in this case. So you, for example, if you were doing a Z2 symmetry, naively you would say you have two sectors, the even and the odd sector. But we're also including symmetry twisted boundary conditions. So in addition to having even and odd, you can also have periodic and anti-periodic. This is also described by the symmetry, and in the end you end up with 4 sectors. That's not surprisingly, they correspond. Sorry, is there a question? Yeah. Okay. If not, then is there a question or no? Okay. So these 4 symmetry sectors of a Z2 symmetric model, they correspond to the 4 anyons of the toric code, for instance. So the Z2 even periodic would correspond to the vacuum excitation, the Z2 odd periodic would correspond to electric excitation, and so on and so on. So this is no coincidence. And from the tensor network point of view, from well, also from the category theory point of view, these sectors are characterized by cube algebras. This is something that I will not go into too much. I'm happy to explain this if there are any questions about this.
I have a couple of questions.
Yeah, sure.
So first of all, like a priori, do the symmetries have to form a fusion ring, or could it be just something you can work?
Right, you mean something where these NABCs are whatever, right?
Yeah.
Some algebra.
Yeah.
We are using it like this because this is the only way you can guarantee that these symmetries will represent the same fusion ring for any number of sites. So we want to be able to kind of coarse grain or fine grain the symmetries such that you still get the same fusion ring. And it turns out that you can show that this can only happen if you have integers.
Oh, really?
Right. So really these integers, they arise because, okay, again, this will come later, but these integers, they arise because you are taking a trace of some direct sum of matrices. And so essentially these integers are counting the number of times a certain block appears. And in that way you get integers. But if you didn't have something like integers, so you could say, okay, I multiply these integers, so these operators by some number, then this number, well, this would depend on the system size. So you would get something different for different number of system sizes. So this is the only way, which you can show from some tensor network arguments, this is the only way you can make it work, such that this NABC doesn't depend on the system size.
And now in a general system, we could have an infinite number of these.
Exactly. Yeah. So either you say, I have a finite amount. Okay, right. There's 2 options, right? There's a finite amount of them, which is preferable for us because then you can put things on the computer, right? But yeah, you're right. For something like SU2, this stuff also works for SU2. The category theory for something with an infinite number of objects is a bit more shaky, or at least my knowledge of it is. But certainly, yeah, indeed, it also works. Like this could be, these symmetries could be labeled by EREPs of SU2. In which case we get like 1/2 times 1/2 is 0 plus 1.
Yeah.
Right. But you have an infinite amount. Or it could be the group elements of SU2, which you have
In which case you have uncountable.
uncountable amounts. So this stuff also works. I'm going to restrict to the finite case just because it's a bit more rigorous, but we do actually have an example of something where you have an infinite amount of symmetry.
And in the case where it's a fusion, when you're not just a group,
right?
What do you say is the fusion representation? When you decompose over this EREPs, you just think about it in context where you have groups.
Right. I'm still talking about. But that's exactly what is done with these 2 algebras. So you still have some action of the symmetry. You can still construct projector onto different irreducible representations. So okay, for a group, these symmetries they form a group, right? More generally, they form an algebra, and you can still block diagonalize this algebra, and that gives you then the reducible representations. So that stuff all still works for algebras as well.
Okay.
It's like if you, yeah, there's the notion of these guys that form a ring. There's the notion of modules over a ring, and there's a notion of simple modules over a ring. So instead of irreducible representation, I might have used simple modules. If you're more happy with that, that's also completely fine. Right. Any other questions? Okay, great. So let's talk about dualities. What do I mean by dualities? Dualities are maps between models that are seemingly different, but do actually have the same physics. So they relate distinct realizations of the same physics. Some well-known examples of these are something like wave-particle duality in quantum mechanics. Maybe even the most famous one here is the holographic type of duality. So the area CFT corresponds, or closer to this thought, the correspondence between Chern-Simons series and Western theories. And then maybe the oldest type of duality, and actually the one that's going to be a relevant notion for this talk, is the high-low temperature duality of the Ising model. So if you write out the partition function of the 2D classical Ising model, there you can either write this out in terms of spin degrees of freedom or in nominal degrees of freedom. This is the high-low temperature expansion. This is duality called the Kramers-Wanier duality. For the Ising model, this was a very useful duality because it allowed Kramers and Wanier to exactly determine the critical point before the Ising model was exactly solved by Onsager a few years later. So the critical point of Ising was known just by this duality, by enforcing that this duality becomes a symmetry. They were able to determine this critical point. So dualities are useful. Actually, Ising model was then later solved by a mapping to, can very easily be solved by a mapping to free fermions, which is the Jordan-Wigner transformation. And we will see that is actually also just a kind of duality. So dualities are useful. So more concretely, we characterize duality as follows. A duality is something that maps local symmetric operators. The prime example of this are your terms in the Hamiltonian. These are symmetric operators. To dual local symmetric operators. So a duality is a map from a local Hamiltonian to a local Hamiltonian. Furthermore, a duality is something that maps local order operators. So an order operator is an operator that is not symmetric to a dual non-local disorder operator. So in case of the Ising model, this would be, we could take sigma z, spin operator, which would be an order operator. Under the duality, this would be mapped to a string of sigma z, which would be a domino operator, which is a non-local operator. And it is implemented as an isometry between the dual Hilbert spaces. So the duality is an isometry that relates one Hamiltonian to another Hamiltonian, which implies that they have the same spectrum up to the generacies, which is why we're saying it's an isometry and not a unitary geometry. Okay, good.
There was a question
Right.
about whether, well, what fusion ring or symmetry twisted boundary condition, if you could sort of briefly describe what that was, whether it's important, if it's important for.
It's not going to be particularly important for this talk, but if there's time at the end, then I can go into this in a bit more detail. Yeah, sure. You can think of it, the symmetry twisted boundary conditions. So these symmetry operators, we will see they will be represented as matrix product operators. And in this way, they act horizontally. Symmetry twisted boundary condition would just be, I put an MPO vertically. So before I put my thing on periodic boundary conditions, but before I glue my Hamiltonian together, I put one of these symmetry twists in there. And this interacts with your different sectors. And if you want to talk about how the symmetry acts on these twisted spaces, you need to consider cube algebras, which are something that I can explain a bit later if there's more time.
I have a quick question about
Yes.
Right? So here you say it's the fusion ring is not group. So in general, it's OA. Is it still operated, but it's not unitary?
Yes, indeed.
And how does it look? Do you have any example? So how does
Yeah, the Fibonacci symmetry. So the tau particle in Fibonacci, this would be O tau times O tau would be the identity operator plus O tau. This is not an invertible. So we are not requiring that these symmetries are unitary. We are just saying the only requirement that we're putting on here is that the
So what does O tau look like? Is the ribbon operator of the tau?
sort of, yeah. And in the end boils down to that, but I won't talk about it in that language. But indeed, that's what it is exactly that. It's the Wilson loop operator corresponding to the tau. If you think about it from the topological order point of view. Right. So where were we?
Are you going to assume that your Hilbert space is decomposed as a tensor product of local Hilbert spaces? Or you don't?
I'm going to assume something like this, but in general, the Hilbert space might not be a tensor product space. So for example, a model that we could study in this language is these golden chain Hamiltonians. That's probably what you're asking, right? Because we're talking about Fibonacci. This is not a tensor product, but that's also included. Yeah. Okay. So your symmetry splits your Hamiltonian into different sectors, simple modules of the this tube algebra, if you like. And what your so these different symmetry sectors, they have to match between the two dual models. This is something that you can guarantee by the fact that okay, our construction will exactly guarantee this, and the duality will map between one sector of one model to a dual sector of another model. But these sectors themselves, they need not be the same size. So the dimension of these simple modules doesn't necessarily have to be the same size. And for that reason, a duality in general is an isometry. Because the dimension of your Hilbert space of one model compared to the dimension of Hilbert space of another model, of a dual model, might not be the same. The reason is that these irreducible representations of your symmetry don't have to be of the same dimension for between dual models. Okay, so as I said, my point of view on this is I'm coming from this from a tensor network point of view, which is not essential for understanding the construction here. It's not like we could not have done this without tensor networks. It just gives a very convenient language, just like the quantum circuit language. Quantum circuit pictures are a very useful language to do quantum computation, and tensor networks give you a very nice and efficient language of drawing diagrams, making Hamiltonians, looking at how symmetries act on these Hamiltonians. So we are defining our Hamiltonian as a sum of local terms, these little HAI, where we will write this Hamiltonian as a tensor network. So what this means is that we are looking at this Hamiltonian. It acts on this on the gets I and L, which would be multiple, and maps these to gets I prime and L prime. Now these guys, this is just a way of expressing the coefficients of this operator, this matrix element. So this is tensor network language, and schematically we draw this as you have these two tensors, A and A bar. It has to be A bar because we want this to be efficient. They're contracted along this like any Hamiltonian you can write in this way. You can think of this as a genetic Hamiltonian would be like a 2-qubit unitary, but it doesn't have to be unitary in general. And you could do an SVD on the unitary to something like this. So a generic Hamiltonian can be written in this form. This is completely general.
Positive semi-definite spectrum.
I want it to be,
Or is it sum of the K? Eigenvalues.
well, I can just take any operator, do the SVD, and I'm not requiring any.
A bar is not complex conjugate of A, it's just like some other tensor.
It is complex conjugate because I want this to be a Hermitian operator, which requires me to.
So it looks like, yeah, I agree, it has to be positive. Am I
Uh,
feel like I'm going to
Maybe not, because she's not
No, right.
multiplying A times A bar in the seeds such that he's taking a matrix element of A and a matrix element of A bar.
right.
So anyway,
It's
you
not.
can have negative
No,
eigenvalues.
it's not A times A dagger, right?
Yeah.
Well, I mean, it sure looks like it to me. If you group IL, the primed IL, the unprimed
Yeah.
IL, and right, that's one index and
Right.
another index, and it's A dagger or AA dagger.
Yes, indeed. So it does look like A times A dagger. So indeed, there's something wrong with this.
Well, that the sum over A, that they're all positive. A dagger is positive semi-definite. So sum of positive semi-definite is positive.
No, indeed. If you just so what you're saying, right, is you group these guys together, group these guys together, it's just A times A dagger, where A is a square matrix necessarily. Indeed, that is a positive.
And that's exactly the group you suggested by your brother.
Yeah, exactly. So there's something wrong with this. So there should be should be slightly different to have it be Hermitian. This is the first time I've got this comment. So,
Wait, why wouldn't it be permission as stated?
it's Hermitian, but it's also positive.
Right,
And I don't necessarily
Okay.
want it to be positive.
so you just need a coefficient next to.
Yeah.
Like that, constant, right? Of the constant.
Yeah, sure. I mean, you say you can shift any Hamiltonian to be
Yeah.
constant. Yeah, sure. Yeah, that's like a hot fix. We will address this. We will address this one. Yeah. Thanks for that. This is the first time. So this is the first time I'm giving this to like a quantum info audience, so I should have expected as much. Thanks. Right. It's really not important for the story, but thank you. So in this language, we represent the symmetry as a matrix product operator. The matrix product operator is something that looks like this. This is an operator that is a product of matrices. So for those of you that are familiar with matrix product states, matrix product state is a state that is a product of matrices. A matrix product operator is just an operator that can be expressed as a product of matrices, which is written diagrammatically like this. So the fact that this is an MPO symmetry implies that I can pull this symmetry through this tensor A. And I can also pull it through the tensor A bar, such that I can pull this entire symmetry through my Hamiltonian. A duality then is represented as also as a matrix product operator, but as a matrix product operator intertwiner, which is drawn in blue here. And it looks very similar to this matrix product operator symmetry. But what it does is if you pull it through this tensor A, which builds up some model A, you pull it through, it maps it to some tensor B, which is the tensor that builds up the dual model. And then this dual model also again has an MPO symmetry, which is not necessarily the same symmetry, original one, which is written there in this last equation. So it's just again an MPO symmetry that you can pull through this tensor B, which describes the symmetry of the dual model B. And again, these symmetries before and after duality do not necessarily have to be the same symmetry. For Ising, they would both be a Z2 symmetry. For Jordan-Wigner, they wouldn't exactly be the same. Here it would be the Z2 symmetry, there it would be the fermion parity. If you're doing a generalization of Kramers-Wanier to a non-abelian group, you get a group symmetry here, and on the dual side, with a symmetry that corresponds to the representations of that group. If your group is non-abelian, then G and rep G are not the same. So these are kind of the things that can happen with duality. Right. So how does this work? Let's consider the finite group case just to get some idea of what these things look like. So if I take a three-leg tensor A that's symmetric under some finite group G, what this means mathematically, that there's some representation U3 of G that I can pull through this tensor A, so turn into U1 of G, U2 of G. So each leg of this tensor transforms according to some representation of the symmetry. I could put this guy on this side because these are unitaries here. Make it more clear that this tensor is invariant under the symmetry equation. Yes.
So in the previous line, you have electron leg connecting different blocks.
Yes.
Yeah, but here you know that it's
Because I'm considering a finite group for now. I'm talking about the usual symmetry case that perhaps you are more used to, which are just tensor products of local representations. And a tensor product is the same as a matrix product operator of one dimension one. So a tensor product is just a contraction along a one-dimensional index. And that's why I don't have the line here. You could draw a line, I could have drawn lines here, but they would have been one-dimensional, so they wouldn't do it. That's why I'm on. Yeah, it's a good question.
This is called covariance, by the way.
Sure, yeah. Right. Well, okay, so when you UG are some representation. In general, any representation decomposes into a direct sum of ERAPs. So all of these are G's. So combination of irreducible for it's connotation for irreducible representations of these Wigner images. Then there's a theorem that states that A must be built from categorical coefficients. So if A transforms covariantly under symmetry, it must be of the form given here, where this tensor A is some linear combination, where the coefficients of this linear combination only depends on the ERs of some Clebsch-Gordan coefficient. That's a general theorem. It was proved, well, Wigan and Eckert proved this for SU2 way back in the day when they were thinking about transition amplitudes and showing that if you compute the matrix elements of some operator that transforms according to some representation of SU2, I can only get certain combinations of, I only get non-zero if I'm looking at this in certain states. And well, in essence, they found that there's a Clebsch-Gordan coefficient being there, and this kind of this theorem is more generally it states that if I have an operator that transforms covariantly under my symmetry, then it's a linear combination of Clebsch-Gordan coefficients. Right. So some group theory now, these Clebsch-Gordan coefficients, they are recoupled using F symbols or 6J symbols, as you might be more used to. Which looks like this. As an equation, it doesn't really give much insight, but as a picture, this equation looks like this. So what these 6J symbols are doing is it's telling you how the fusion of ERs, these Clebsch-Gordan coefficients describe how to fusion, how the tensor product of two ERs. What operation do I have to do to again write this as a direct sum of ERs? That's what Clebsch-Gordan is. These F symbols or 6J symbols, they are telling you how taking first this second one and the third one, and then the first one differs from doing it the other way around. So it's telling you something about the associativity of computing the fusion of these ERs. The M's don't appear in this picture. So that these tensors here, this tensor, this leg, is labeled by J2. But as a tensor, this thing evaluates two Clebsch-Gordan coefficients. So this leg here is the dimension of J2 dimensional. So this is not the matrix index of this tensor, right? You see here in this equation, the M's, they are all external indices. Well, here they are contracted over. And also here they are contracted over, and this contraction is just this here, this contraction between these two guys. The contraction and 5 here is contraction between these two guys. That's just the tensor network contraction.
But why not just have JM, one input and output?
Oh, sure, yeah, I could. It's just to emphasize that, yeah, this equation here, this guy,
And so then if it is like JM, can I think of these as ERFs and you're fusing them and there's an associativity to fusing them?
yeah, exactly, that's right.
That's literally.
Yeah, this F or 6J symbol is associated with fusion of the tensor product of EFs. That's what a 6J symbol is. Now, those of you that have worked with tensor network before, or in particular have worked with symmetries in tensor networks before, these F symbols actually allow you to compute arbitrary symmetric tensor network contractions. So a symmetric tensor network, by definition, has to be built from these Clebsch-Gordan coefficients. Now you can imagine that I made some very complicated diagram like this. And let's assume that there are no open indices anymore. I can completely contract that diagram only using these rules and the orthogonality of these Clebsch-Gordan coefficients. So this, for a symmetric tensor network, this is the only piece of data you need to know to be able to perform any kind of contraction. For example, if you were computing the expectation value of some observable or the energy of some state, right? You're computing the overlap between some states and a Hamiltonian. This has no closed images. This should just give you a number. You can compute this only using this guy. So one application of this using these F moves to evaluate these diagrams is that you can consider the algebra of all symmetric operators, which by definition should look something like this. It's going to be some linear combination of these categorical coefficients. We call these bonds because well, there were some previous papers by Gerardo Ortiz on dualities, and they had a similar construction where they call these things bonds. I've asked him why he called it bonds, and there's really no good answer. So let's just, if you have a problem with this, then I suggest that you contact him directly and ask him again, because I will not get a good answer. So we call these bonds, and these bond algebra just has elements given by the identity. It's all of these possible bonds here, so these are these guys, but it's also all possible products of these guys. So I'm allowing myself to take this bond algebra, this algebra of symmetric operators. I'm considering all possible products of these guys. This generates some algebra, which we call the bond algebra. So in particular, this bond algebra contains all symmetric Hamiltonians, but more generally, it just contains all symmetric. This one?
No, right.
This is so any bonds here, any element of this symmetric operators has to be a linear combination of categorical coefficients. So these guys now are the categorical coefficients, as in the previous picture. This is just saying there's some linear combination of categorical coefficients. Any operator of this form will be symmetric via the previous slide, right?
And sum over only particular JN.
So I can take this guy to be whatever I want. Yes. This is just any function of, so I could say I'm summing over all of them here, but I could say it's just 0 for some combination. These numbers just determine how much weight do I give to each possible combination of the chain. This is a generic two-body symmetric operator, is always of this form. Right. So if you go to some basis now, because of course this bond algebra is, well, if you're assuming that you're on an infinite number of sides, this is going to be countably infinite, well, even on finite sides, it's going to have a countably infinite number of operators. But you can go to some basis. So it's not like any, if you're just taking products of these guys, you're not always going to end up with linearly independent objects. At some points, you're going to find back the objects you already had. So you can go to some basis for this bond algebra, which you call QuiCS here, which I realize now are the same notations I use for the symmetry, which is bad. So forget that I use this as a notation for the symmetry. And in this basis, because it's a basis, the product of two of these basis elements has to be expressible as again objects in this basis with some structure factor here. So this is the structure factor of this algebra, telling you how the product of two decomposes as a sum of them. Something like an operator for expansion. Familiar with that. But the important thing is that the structure factor, this little f, only depends on the f symbol here. There is no information on these categorical coefficients in there. There's no little m's in this thing. It only depends on these f's, precisely because I can compute the products of these diagrams only using these coupling groups. And so with this observation, what we claim is that for a given set of f symbols, or for a given algebra of symmetric operators, there exists distinct sets of categorical coefficients that are recoupled by the same f symbols, so that we generate you the same algebra. It means that they generate isomorphic bond algebras, and these different sets of categorical coefficients are what's going to give you a dual Hamiltonian. So your Hamiltonian itself, of course, depends on these categorical coefficients, because it's just a linear combination of categorical coefficients. But the point is that there are different choices of categorical coefficients, and I should say generalized categorical coefficients, because of course, there's only one categorical coefficient. There's different choices of generalized categorical coefficients that are recoupled according to the same recoupling theory, which means that the algebra these different terms generate is going to be the same. That's something that you typically have in a duality. The Jordan ring transformation is a mapping from xx plus z to something where you get the same algebra, but in terms of fermion operators. So this kind of stuff kind of formalizes that a bit, and then shows you what the role of symmetries is in generating these algebras. So this is all nice, but of course this is completely useless unless we can, for a given symmetry, find all these different Dutch coordinate coefficients. And for that, we need a little bit of category. So this is my one slide on category theory that I have. I promise that it's really not difficult, but there's some, well, there's some abstractions that you kind of have to get over. But in the end, if there's one thing you remember from these fusion categories, is that they give you a very nice mathematical packaging for constructing solutions to certain equations, namely Pentagon equations, that are otherwise very, very hard to solve. And it turns out that these Pentagon equations, these equations that we're interested in, that they appear all over physics. So there's many problems you can start thinking of. Like if you just start thinking of symmetries, in the end you will arrive at these Pentagon equations. And it's nice to know that there's a general theory behind these equations, and this theory is the theory of fusion categories. So what is a fusion category? Fusion category D is something that has objects, which you can think of as onion labels if you prefer. These objects, they can fuse together. So a good example here would be the representations of SU2. The simple objects would be the irreducible representations of SU2. The fusion rules would be the fusion rules of the representations of SU2, which are well known. Then there's some F symbols, which in the case of the representation of SU2 are 6J symbols. And these guys, they satisfy some Pentagon, which schematically looks like this. If you've never heard of a Pentagon equation, it's essentially this is the definition of this F symbol. Now, more generally, you can show that if you now consider the product of 4 of these guys, using these rules, you can arrive at a consistency condition for these F symbols, which looks like this, which is the Pentagon equation. This is schematically. If I were more careful, I would have to put a lot of inches here, a lot of sums. I'm not doing that, just schematically this equation. So this is the first ingredient. This is describing the irreducible representations of your symmetry, if you like, in the case of SU2. Now, there's a second ingredient, which, so this guy gives you the 6J symbols. There's a second ingredient which will generate all these different Dutch coordinate coefficients, which is what's called a module category over D. So you consider in the same way that a fusion category is the categorification of a ring, a module category is a categorification of a module over a ring. So if you're familiar with rings and modules over rings, this is just the categorification of that. So what is this? You can think of this as like a representation of the fusion category, in the sense that it is a category here, an additive category which plays the role of the vector space in your module. This additive category has simple objects again, just like this fusion category. And then just like with a module over a ring, you need to define some action of the objects of this fusion category onto this module. This gives you some action rules. So these are like a generalization of these fusion rules. You get action rules. You get some objects of D acting on an object of the module category, gives you a linear combination of objects of the module category. Again, there's some F symbols associated to this module category. And these are the things that generalize the Dutch coordinate coefficients. So for a particular choice of module category, this will give you back the Dutch coordinate coefficients. But more generally, there's other solutions that give you things that satisfy the same kinds of equations as Dutch coordinate coefficients, but they are distinct. And so they couple to this F symbol here via this equation, this mixed pentagon equation, which if you were to plug this in for the 6J symbols, the four coefficients, you would recover this equation here on the top. So you see here that this is bottom form, left Gordon, step times left Gordon. More generally, in a fusion and a modular category, you get an equation like this. So you get this modular associated is F symbol times modular associated. So this generalizes this relation between 6J symbols and left Gordon coefficients. And this is exactly the thing we need to construct these dual left Gordon coefficients. So how do these Clebsch-Gordon coefficients then look like? Okay, this is going to be this sort of a leap of faith. This is, if you are somewhat familiar with this, then this is going to mean something to you. If not, then that's okay. Just the picture we have is that this module associated here, this guy, you can write this Clebsch-Gordon coefficients as a function of this guy. So this is some complicated expression. You have to add some substructure to this tensor here, which I'm not going to explain. There's just, you can write this Clebsch-Gordon coefficient as a function of this module associated. And if you have two different module categories in M1, with a modular associated triangle F, and then M2 with a modular associated triangle with a dot F, then you get two distinct Clebsch-Gordon coefficients. But both of these will satisfy this equation. This equation is also the one we had for the original Clebsch-Gordon coefficients, right? This just generalizes that equations to more general Clebsch-Gordon coefficients. But again, the fact that both of these are recoupled by the same epsilon will imply that the algebra of symmetric operators built from these dual Clebsch-Gordon coefficients is going to be the same. This is not going to depend on whether I choose this guy or whether I choose this guy. It's going to generate me the same algebra. Yes.
We'll go back to this module category. What is that for spins again? Is it just one category with all the vectors, the simple objects in the vector spaces, spin 1 half, spin 1, spin 3?
Right. So in the usual case of the Clebsch-Gordon coefficient, this guy would be representations of SU2.
So matrices.
No, this category here would just be the category of representations of SU2, right? So the objects would be 0, 1 half, 1, 2 half. Right. These are just the simple objects. It's just some abstract thing, right?
Yeah, but I'm relating them to matrices because they're representations.
No, but the representations are going to be, that's an additional ingredient. That's going to be, well, it's going to come. It's on in a few slides, this object will be there. But yeah, for an ordinary group, this would be the 6J symbol. This would be Clebsch-Gordon. This category would be back. It's the category of finite dimensional vector spaces, which just has a single simple object, which would mean that these lines here, they're not there. But these lines, they are labeled by the objects in the module category. But there is just one. You might
That's
as well.
already a key difference, right? Because on the matrix side, or line,
Yeah, sure.
there you have all the EREPs are distinct simple objects, but on the vector side, you don't have the corresponding distinct vector space for each EREP.
Right.
You have this one Lego block,
Yeah.
this one-dimensional block that you can stack to build any corresponding vector space that corresponds to an EREP.
Right. Right. Okay. But the specific EREP that you were talking about, the EREP as a matrix, that's going to come. That's going to be in 2 slides or something. Yeah, the object is going to be. But I think I explained to Chris already how the MPO that you would like to consider fits into this language. Yeah, you can really see that's exactly the same thing. Yes, there was another question.
So,
yeah.
what are those pictures called, like on the left hand side of the,
These pictures?
Yeah.
The way to think about this is that these are tetrahedron. So an F symbol is defined like this. Now what you can do is you can take this stuff here and glue it to this side and build a tetrahedron out of that. And in that sense, this F symbol essentially corresponds to some tetrahedral diagram that you evaluate in fusion. these tetrahedra that you built are exactly these kind of things. So this thing is a tetrahedra. That thing is a tetrahedral. Then the value is to the subset. If you're familiar with state sum topological field theory, you're going to know about these tetrahedra. These tetrahedra are what you use to triangulate your manifold in such a way that the triangulation, that your partition function does not depend on the triangulation, for which you then have these Bachner moves. These Bachner moves are nothing but these F moves. If you are familiar with these triangulations. That's kind of where these things come from in a more topological field theory oriented setting. Right. There was another
Can
question.
you go back to the previous?
Sure.
So alpha, beta, gamma are representations of your symmetry.
Right.
And what are capital A, capital B, capital C?
They are simple objects of this module. So for the case where you recover the usual Gordon coefficients, you would take this module category to be the category of finite dimensional spaces, which is a very formal way of saying this is something with just a single simple object.
Basically, representations act on.
Exactly, that the representations act on. Right, exactly.
And you made a comment about how the duality is implemented within this formalism. Are you going to explain that further?
Yeah, I will explain this. Yeah.
Good. So and that's why you can have more than one category, because you can have this thing act on vector spaces
Right.
or some other rings.
Right. So indeed, so one comment is that one possibility for this, that you just take this to be equal to this. This is a categorification of taking the regular representation. So you can say my category acts
Can act
on
on
itself.
itself.
Right? That's a regular representation. This is always a solution. And in that case, these two absolutes will coincide.
Sorry, but that's just vec. That's just this inside that built out of vec.
No. You're like if this is a group, for instance, right? You take the simple objects to be group elements.
Yeah.
Then the regular representations would be acting. It's your group acting on group elements, right? So the simple objects of this thing also have to be group elements.
You could formulate it as a vector space, though.
But again, it's not.
You don't have to.
It's
So it can be its own thing.
this language of
Okay.
vector spaces. It's not directly there, right? It's some abstract structure. The actual matrices and the actual things you talk about, those are the things you will see in physics. Those are the things you will see in a lattice model. So this is all some well, abstract nonsense, if you like, that does help you solve the equation. But in the end, the important ones is on these substances. And we just choose this to be whatever it has to be to recover the things that you're more used to. So
Regular representation decomposes into ERAFs that act on vectors, so that's why it's confusing to me that the regular rep would not be part of the vec module category.
yeah, I see, but I don't think the analogy between. I don't think you can think of it at that level.
That's,
But okay,
that's the type of generalization that confuses people, I think, as you go to categories.
yeah, I think.
The way they organize it is different.
Yeah, sure. Yeah. Yes.
The fusion category, do you take it like if in the group case, do you take rep G or do you take G back?
To get the thing that you are used to, I would take this to be rep G,
Rep G.
but I can also take it vec G. I can take it to be whatever I want.
And then what's the relationship if you took that
Yeah,
G back, what would happen?
I can comment on that a bit after maybe. So the relation will be that for a given fusion category. I will just move on and then indeed we will see this. So right. So this is what I've said so far, I think, right? So a dual models are characterized by the same fusion category D. This is the fusion category that determines the bond algebra. It gives you the algebra of symmetric operators. This you don't want to change under duality. So this gives you the same recoupling theory, but different choices of a module category, which gives you dual Hilbert coefficients. Yes.
Yeah, so in general, you should have infinite language with this M, right? So that this means you have the infinite family of the duality to your own.
No, there's not an infinite number of M's. So for a given fusion category D, there's only a finite number of distinct module categories that you can choose.
So how is it classified?
It depends. For a group, they are classified by a subgroup and a two-core cycle on that subgroup. More generally, for a twisted group, they are classified by a non-anomalous subgroup and a two-core cycle on that subgroup. For RepG, they are classified by the possible categories of projective representations of a subgroup. For the SU2 level K fusion categories, there's also a classification. It's the ADE classification. And that's about all the general classification results I know. For many,
Case by case?
so it's already hard to classify fusion categories, right? Fusion categories have only been systematically classified for 5 or 6 objects, because what you have to do is solve this equation, and this is a really difficult equation to solve. So there are fusion categories that have been constructed from groups, from group theory. These are G or RepG or twisted groups. And for those, the module categories have been classified, because there you can map the problem to something in group theory, and there it's been done. There's also the class of fusion categories that come from quantum groups. This slightly generalizes this. These are the SU2 double Ks. For these, the module categories are also known. But then there's also just fusion categories that exists by themselves that have no relation to any group theory or quantum group theory constructions. The simplest example would be these Hagerup fusion categories. And for those, you just have to solve this equation to find the possible module categories, which is a very hard equation. I think the subfactor people, they have some tools to deal with these kinds of questions. But in general, it's just a very hard problem. Yeah. But what is true, what you can prove, just like for fusion categories, is that for a given set of fusion rules, if it's finite fusion category, there are only a finite, or at least a discrete set of solutions. There's like some rigidity to these F symbols, such that you can, there's only a distinct number of gauge inequivalent solutions to these Pelton equations. It's called Ocniano rigidity. Right. Was there another question, or okay? So I think it was here, right? Okay. So again, dual models, same fusion category B, different module category M. Consequence of this is that the algebra of symmetric operators is the same. These dual models have equivalent but distinct realizations of these symmetries, which we denote by another fusion category C. And its fusion category C is completely determined by the choice of M. A very technical way of saying this is that C is given by the category of the module vectors from M to M. That's not going to mean anything probably to most of you. It's just know that for a given choice of D and M, you can compute the symmetries via some categorical tricks. So those give you the symmetries, but also you can compute the intertwiners that relate to models. You can also construct these from the categorical data. Again, this is some computation category theory that at the end is not hard, but it takes some backgrounds to set this up.
That's like super general. That means that there's like some group acting on a vector space and the same group acting on a ring of polynomials. There's some symmetry that intertwiner that can.
So you're talking about it now again at the categorified level, right? You're just talking about rings acting on vector spaces and different possible vector spaces. I don't know.
No, I picked the ring because it's a different module. It would be a different module category.
Right. Okay. So you're talking at the level of categories. Okay.
So there's 2 different categories, which module categories, which to me are like things this group acts on. Okay.
Yeah, sure. That's
and there's different. They're very different.
Right.
So how can you go from one to the other?
Right. You can compute this.
You can't always. Okay? The modules can be so different.
Yeah, you can always compute this. It's a linear problem to compute the data that problem is. But this is requiring the knowledge of module functors, which again is some additional categorical ingredient that I don't want to get into too much, but it does provide you with the tools to be able to compute these kind of things. So right, what does this MPO intertwiner look like in general? It's an object like this. It's again one of these tetrahedral diagrams, just tetrahedral drawn in a slightly different way. And this data is the thing that you can compute from these two guys for any choice of modular category. This guy, you see that on top, has the choice A1, B1, this is modular category. One on the bottom is different modular category. So this guy satisfies this equation. It's called the pulling through equation. It's the more detailed version of this guy. And then what it will do is it will map categorical coefficient of type A to a categorical coefficient of type A. These things you can construct for any two choices of modular. It's a fairly straightforward computation to compute these things. Now a special case of this is where we take both of these to be the same. And then this is what we call a symmetry, right? A symmetry, you can, in some weird way, maybe some roundabout way, you can think of a symmetry as a duality between a model and itself. For which then you can compute this thing. And this is the thing that if you do this for FG module category to be back, this would give you the EDAP matrices that you're interested in. So that's answer your question, Lucy, I think. I'm not explaining explicitly how to compute this, but for any given choice of modular category, you can compute this. They satisfy an equation.
Maybe we can keep going, but maybe you want to.
Yeah, sure. So
5
that's,
minutes or so.
so this is my I was going to do examples, but I'll skip this. So just to briefly flash what kind of examples you can do like this. If you take D to be a D2 symmetry, then there's 3 different choices you can make. You can either get the transfield, you can get it ground when you do, or you can get fermion. If you take a Z2 times Z2 symmetry, there's actually 6 choices you can make. I've only listed 2. For one choice, you can get, for example, the spin-on Heisenberg model, which you know is a non-trivial SVT in the ground state. It's a holding phase. For a different choice, you can get a dual model to this. You can get a duality transformation from the spin-on Heisenberg model to some other model. It's called the Kennedy-Tasaki dual of this model, which is a trivial. So this way, you get a duality between something that has SPT order and something that has trivial SPT order. And then there's some more exotic examples. Well, you can take D to be the Ising symmetry. So this is Z2 symmetry plus the ground self-duality imposed as a symmetry now. This necessarily gives you the critical Ising model because you are requiring this ground duality to be a symmetry. So one choice is just this, which gives you the Ising model. And another choice is fermion condensed modular category of Ising, which gives you massless free fermion. And then you can do the same with 2 copies of this. So you can get either 2 copies, 2 decoupled critical Ising models, or you can get an XY model, or you can massively fermion. Some more exotic examples, and this is the example where you can an infinite number of the projects. You can take D to be the representations of the quantum group SL2. For a specific choice, you get what people call the solid on solid models. For those of you who have ever looked at integrability, you might know these. For a different choice, you get a 6 vertex model or the XXZ model. And then there's this exotic category that I also explained, which just exists in and of itself. So all the previous examples can be studied via group theory techniques. This one is impossible to study using group theory. You really need fusion categories to understand this guy because it can only be constructed via fusion category techniques. So there's been some recent interest in this model. We have a paper on this together with Rebecca, Martin, Ramona, Tobias, Gito, Frank, and then there was at the same time a paper by these people where there was some question: is there a critical lattice model that has these symmetries? And these 2 papers seem to indicate that this is indeed the case. But for this exotic model, we can also construct the dualities. But for this model, they don't really have a name, so that's why the question marks. So my final slide, and to conclude, and it is nothing else that you remember of this talk, then I would say that this is the most important conceptual part to me, is that lattice models have 2 aspects. There's like a topological aspect of a lattice model and a geometrical aspect. The topological aspect is about symmetries, symmetry sectors. What kind of order parameters do I have? How do the string order parameters look like? But importantly, also, what are the dualities? It's also part of the topological information. And then there's the geometrical data, which is telling you about okay, what kinds of models can I make, like which specific symmetric operators do I choose? What are the correlation functions? Is this model critical or not? What are the scaling dimensions? Is this model integrable? Those are all more like geometrical features. And so the message is that the topological part you can completely understand using this category theory. So this gets you a lot of insight into this model, which gives you very nice. Well, it gets you sets you up in a way that you're potentially able to answer these kinds of questions also in a more efficient way. Of course, you know that if you want to simulate a system, you want to use all the possible symmetry. What the dualities allow you to do is, for example, if you want to study a model, you could equally well study a dual model that might be more easy to implement. Good example would be the Ising model, right? You do the Jordan-Wigner transformation to free fermions, it becomes trivial. So in that sense, dualities can help to answer questions also on the right side of this diagram. So an outlook is, of course, the obvious question is do this in higher dimensions. And conceptually, this works. The category theory is almost there. This is still somewhat under construction from the math side even, but this is most of the way there. And it's clear how to generalize all of these things to higher dimensions. Maybe one paper to highlight there is a paper by Clément, where he generalized these different tensors that I showed to the case of fusion two categories for some very particular kind of fusion two category and showed how all of these things work. So with that, I think I am finished. Thanks for your attention. If there's any more questions, I'm happy to